Atomic structure. Three particles of atomic structure. Atoms are the definition of atom. Atom are the smallest unit. Atom are the smallest unit of matter that retain the properties of an element. They are composed of three fundamental particles: proton, neutron, and electron, each with unique properties that contribute to the atom's overall behavior. So the three subatomic particles of atom are proton, neutron, and electron. Number one is the proton. Proton. Now, where is proton located? Proton and neutrons both are located in the nucleus. So proton is located in the nucleus, the dense core of the atom, and it has a charge positive. So proton has a positive charge, while neutron has a zero charge. And mass of one atom, well, mass of proton is almost equal to one atomic mass unit, which is equal to 1.67 times 10 to the power minus 27. And also for the neutron, it is same 1.675 times 10 to the power minus 27, slightly heavier than proton, like very slightly heavier. Now, what is the relative size? Much larger than electron, but similar to neutron. So for protons, they are much larger than neutron. Same for much larger than the electron, but similar to neutron. Its function. It defines the atomic number. What is atomic number? Atomic number is the number of protons, which actually identifies the element. For example, let's say we say carbon atomic number is carbon has 6 protons. That means its atomic number is 6 as well. The number of proton determines the chemical identity. The positive charge attracts the negatively charged electrons, keeping them in orbit around the nucleus. Now, function of the neutron. It adds mass to the atom without affecting its charge. So the neutron has no charge, but still it adds mass to the atom without affecting the charge. Acts as a nuclear stabilizer by reducing repulsive forces between positively charged proton. And isotopes are atom of the same element with different number of neutrons. For example, let's say carbon 13 and carbon 14. Carbon 13 has 6 proton. Carbon 12 has 6 neutron. Carbon 13 has 7 neutrons and carbon 14 has 8 neutrons. That means they have different number of neutrons. Now electrons are surrounding the nucleus. So they are surrounding the nucleus just like the moon surrounding the earth, or the sun surrounding the moon, the earth surrounding the moon. So let's say, for example, this is the nucleus. In the nucleus we got proton and we got neutron, and around the nucleus we got electron in the shell. Okay, the electron mass, it is 9.11 times 10 to the power minus 31, which is very small, which is compared to proton and neutron, it is 1 divided by 1836 times smaller. Its function is responsible for chemical bonding and reaction arranged in energy levels, shells, and it following the Aufbau rule, Pauli exclusion principle, and Hund's rule. We will discuss them in the next slides. Now, extended atomic structure and concept, electronic configuration orbitals. Electrons occupy discrete energy level, n is equal to 1, 2, 3, and are distributed into orbit SPDF. For example, let's say oxygen electronic configuration is 1s2, 2s2, 2p4. Forces inside the atom: strong nuclear force, electromagnetic force, and weak nuclear force. What is strong nuclear force? It binds protons and neutrons in the nucleus, overcoming proton repulsion. And electromagnetic force attacks electron to the positively charged nucleus, while the weak nuclear force is responsible for radioactive decay process, for example, beta decay. And now isotopes and ions. Isotopes, same number of protons but different number of neutrons. For example, hydrogen has three isotopes: protium, deuterium, and tritium. Protium has zero neutrons, deuterium has one neutron, and tritium has two neutrons. Ions. What is an ion? An ion is atom that have gained or lost electron. So, for example, cation, if an element has lost an electron or more, it is known as cation. For example, let's say sodium. Sodium Na plus ion, which means it only lost one electron. Anion is the gain of electron by an atom. For example, chlorine gain electron. Quarks, the building block of protons and neutrons. Protons and neutrons are made up of quarks held together by glucons. For example, proton 2 up quarks 2 plus 2 divided by 3 each plus 1 down quarks 1 divided minus 1 divided by 3 total charge 0. 1 neutron is 1 up quark 2 plus 2 divided by 3 plus 2 down quark 1 divided by 3 equal each. So total charge is equal to 0. Atomic number and mass number. What is atomic number and what is mass number? Atomic number is the total number of neutrons present in the nucleus of an atom. It is denoted by Z or Z, and the atomic number defines the identity of an element. So the identity of an element is given by the atomic number by the proton, because the neutron and electron can change. Because let's say if there's isotopes which have different neutrons, or let's say there's an ion which can lose or gain electrons, so the proton can never be lost again. Proton will always remain the same. In a neutral atom, the number of electron equal to the number of proton as well. For example, hydrogen has 1 proton, so the Z is 1. Carbon has 6 protons, so is 6. Oxygen has 8 neutrons, so Z is atomic number is 8. The mass number is the total number of proton plus neutron in an atom, and it is represented by a symbol A. The formula for mass number is atomic mass or mass number is atomic number plus neutron, where A is the mass number, Z is the atomic number, proton, and N is the number of neutrons. Example, let's say carbon 12. Carbon has 6 proton and 6 neutrons, so its atomic number is 12. While carbon 14 has 6 proton and 8 neutrons, so its atomic number is 14. Atomic mass is 14. Isotopes. What are isotopes? Isotopes are atoms of the same element which have the same atomic number, Z mean atomic number, but different atomic mass. So, same atomic number but different atomic mass due to a different number of neutrons. For example, you look at carbon 12 and look at carbon 14. Carbon 12 got 6 proton and carbon 14 got 6 proton, but the number of neutrons are different. You see here the number of neutrons are different in both. So that's why we say isotopes have the same atomic number but different atomic mass. Because if we see, both have the atomic number 6, but the first one has atomic number 12, atomic mass 12, and the second one has atomic mass 14. All right. Now look at here. This is the carbon atom. Let's say. So the small number will always be the atomic number, which is equal to the number of proton, and the big number will always be the mass number, which is equal to the number of proton plus neutron. And C is basically the symbol of element. Isotopes. Isotopes of atom of the same chemical. So are atom of the same chemical element. They are the same chemical atom that identical number of protons but different number of neutrons within the nuclei. The variation leads to different atomic masses but does not significantly alter the element chemical behavior, because it does not chemically alter the chemical behavior, because the chemical behavior is usually given by the electron, while the physical behavior is usually given by the neutron. So if there are two neutrons, their physical behavior will be different, but chemical behavior will be same, because in the isotopes, the number of electrons remain the same. Now atomic number, number of proton in the nucleus. Atomic mass is the number of proton plus neutron. Neutron is equal to A minus Z. Atomic number minus atomic mass. Atomic mass by atomic number. Example is same in neutral atoms, leading to similar chemical properties. For example, carbon isotopes, natural and radioactive. Carbon 12 is natural isotope, while carbon 13 and 14, usually the carbon 14 is very radioactive. Carbon 12 has 6 proton, carbon 13 has 6 proton. Carbon 12 and carbon 14 both have a 6 electron, while carbon 12 has 6 neutron, and carbon 13 has 7 neutrons. And stability, carbon 12 or 98.9% natural abundance and stable, while carbon 13 is also stable but its natural abundance is only 1.1%. Carbon 14 is radioactive isotopes and it has 8 neutrons and it is unstable. Half-life is 5,730 years and it is used in radiocarbon dating for ancient artificial and fossils. Types of isotopes, stable isotopes and radioactive isotopes. Stable isotopes, they do not decay over time, while the radioactive isotopes are unstable and nuclei that decay over time. Example are carbon 12 and carbon 13, and here the example of carbon 14 and uranium 238 for radioactive. Used in studies like isotope tracing in biochemistry, while radioactive isotopes are used in radiometric dating, medical imaging, usually used for cancer therapy and etc. cancer treatments. Isotopes in real life has medical application. Iodine 31 is used in thyroid treatment, and technetium 99M is in medical imaging and archaeology. Carbon 14 is in for dating organic remains, and uranium 238 for dating rocks. In environmental science, isotopes like oxygen 18 is used in climate studies. These are the isotopes of phosphorus. They both have the same number of protons, 15, but different number of neutrons, 16, 17, and 18. Electron structure of atoms of various elements. Key concept of electronic structure. Now, the number one is we got electron levels, which is known as the shell, and then the subshell. So, electron occupies energy levels denoted by the principal quantum number. N is equal to 1, 2, 3, 4, and it could be 1, 2, 3, 4, 5, 6. And each level holds the maximum number of electrons. Maximum electron per shell is 2n2. The formula is 2n2. For example, the n shell is 1. So the 2 into is 1, so maximum 2 electron. Now, for example, let's say the second shell. So 2 into 2, 2 and 2. So is equal to 4 times by 2, which is equal to 8. So the second shell can hold maximum of 8 electron. And same for the other one, 2 into 3, 2, which is equal to 18. Now subshells. Each energy level contain levels sublevel like SPDF with varying shapes of capacities. S is spherical, P is dumbbell shape, D is cloverleaf shape, or we call it dumbbell shape, and F is complex shaped. And S can have maximum 2 electrons, while P can have maximum 6 electrons, D can have 10 electrons, and F can have 14 electrons. This is the Bohr atomic model in which we can see that this is the nucleus in the middle, then there is the K shell, which is the first shell, then there is L shell, M shell, and N shell, and so on. Orbitals. Orbitals are sublevels are divided into orbitals, each holding two electrons. So orbital can have maximum of 2 electrons. Electron configuration rules. There are three rules for electron configuration: the Afbah principle, the Pauli exclusion principle, and the Hund rules. So the Afbah rule says that electrons fill lower energy levels first, for example, 1s before 2s, while the Pauli exclusion rule says that no two electrons in an atom can have identical quantum number, meaning each orbital hold a maximum of 2 electrons with opposite spin. The spin has to be opposite. For example, let's say like this. Spin has to be opposite. While the Hund rule says that electron occupy degenerate orbital like the 3p orbital singly first before pairing up. For example, hydrogen H is 1s2, carbon is 1s2, 2s2, 2p2. Arrows representing electron spins. For example, for oxygen, look at here. You can see here that each orbital has 2 electrons and the spins are totally opposite.